Hey everybody, we're going to continue our journey here of learning some of the notations and nomenclature of neural nets and machine learning. And I'm going to share with you one of the things that bothered me when I first started studying neural nets really close. Is like, how can a set of linear equations, we've kind of covered this, it's a weight times an input, and that's linear. How can you use that to model a nonlinear features or nonlinear behavior? So let me discuss that with you. Let's start out with analyzing a simple two-layer neural network. So here's our representation for it. We've got our input layer, and then we've got a hidden layer 1 and a hidden layer 2, and then we have an output layer. And let's zoom in on the hidden layers. So here's the two hidden layers. And as just discussed, the input here is linear. We've got a weight times the input value, and then plus a bias. Now the nomenclature, the notation for neural nets is the standard is that the superscript is a 2, and then the subscript is 1, which is the row. So the superscript is the layer, and then the subscript is the row. So if we had multiple features or inputs, x's here, the next input feature would be x1 for superscript, row x2, which would be the row. So we're just looking at one row here, one simple neural network. So let's show a little bit about what the calculations would be. So if we multiply the weight times the x plus the bias, that gives us this term, which is the out 1, and then we would then use that as the input to the second layer. So that would end up with another weight being multiplied by another bias, in this case superscript 2, which is layer 2, row 1. And then we get an output. If we calculate everything out and wrote it all out into an equation, here's what we get. Out 2 is equal to the second weight times the first weight times the input x plus the bias, and then bias 1 plus bias 2. So notice that W2 times W1 is basically a polynomial, right? And if we extended this further, you can see how layer by layer we're adding more complexity and more nonlinearism to the system. So if we just have one layer, we essentially have a multiple linear regression problem, right? By adding 2 layers, we've added some nonlinearity by multiplying the weights. Okay, so the high-level observation here is by varying W1, W2, B1, and B2, let's just assume it's all one row here. In our simple model, we can represent any number in the real coordinate space. So think about that. That basically means you've got x and y coordinate system. We can go negative, we can go positive, we can have an output value in any one of the 4 quadrants in the real coordinate space. And then even if each neuron is linear, a combination of two or more neurons makes the model nonlinear. And then in a multi-layer network, the weight parameters really make the system nonlinear. That's something to think about. So we think about x's in our normal mathematics as being the nonlinear component. And x's for us are the feature inputs, but what's really nonlinear is the weights. All right, so that's a good takeaway, a good kind of thing to realize. Now, to even give more nonlinear capabilities to a neuron, there's something called an activation function, and this kind of gets into the next level of learning for you and understanding of neural nets, is that we're going to add a nonlinear function to the neuron. So we're going to multiply the input times the weight plus the bias, and we're going to multiply all of that by a nonlinear function. The most common nonlinear function that's used today in neural nets is called the rectified linear unit, or ReLU, and so you can think of everything below less than 0 as being set to 0, and then everything above 0 being set to whatever the value is. So this continues on. So it doesn't clip at the top, it just continues on. So it's linear, everything above 0 and 0 below that. So around 0, you get a nonlinear function, nonlinear capabilities, right? So how you represent this in Python is really straightforward. ReLU function is equal to numpy.max between 0 and, in this case, W1. Oh, I left out the x1 there. It should be W1 times x1 plus B1. So that is the representation of how this would be implemented in Python. I'm going to show you that in just a little bit, and I have it right in my code there. So a note for you is that over time, people have investigated, researchers have investigated a lot of different type of activation units, and that's what this A is right here. It's called an activation unit or activation function. There's the sigmoid data type, and basically that depending on the input times the weight plus the bias, it really scales the output between 0 and 1. The tan H scales the output between -1 and 1. And the threshold is basically a binary output between 0 and some value, and mostly 1. And then ReLU is 0 below, less than 0, and then scale it linearly above 0. So there's some real reasons from a computational performance perspective why ReLU is kind of the common function today. You end up with a sparse matrix, right? You can do a lot of matrix multiplies. And if you have a lot of zeros, that makes computations easier, memory usage lower. And so ReLU is really kind of the activation unit that's typically used. When we get ready to start programming in Keras, you can choose the type of activation function you want. So that's one of the parameters you can choose. So here is kind of, if we go to the next step and we add the activation function, what the mathematics look like. So I've taken the previous value, the previous model here. Here's our equation. And now we're going to add an activation function on the output, apply that to the output from each of our neurons. And so out2, let's look at that, now becomes weight 2 times the ReLU of the output 1. So we're basically taking a rectified linear unit of W1 times X1 plus B1. So that's out 1. And then the ReLU is applied to this function, actually is applied to B2 as well, right? So we've put out 1 here plus the bias, the new bias, and then we're multiplying all of that activation function by all of that, gives us kind of an accounting problem to take care of. And Python does this real well because we can manipulate vectors and matrices very easy. So I think that this is the challenge to most students, is the accounting of the variables and keeping track of everything. But what the high level point here is that the ReLU adds another nonlinear capability. So this is how a set of linear equations can then really create and model nonlinear features or behavior. So let's run a little bit of code here to explain this. So here's my Python code, and I'm in a Jupyter notebook. You have the source code to all of this, so you can go and follow along. So we've got the 2-layer 2-neuron system. I've just simply said neuron 1 is equal to X, weight 1 is 1, bias 1. I've kept it all simple. It's not about the accurate calculation at this point. It's about conceptually, can we understand 1 layer deep on our machine learning neural net so that we can be really good in using the models in the future. So I keep on here. I've got neuron 2, I've got weight 2, bias 2, and so neuron 2 is equal to this equation above, neural 1 output times the weight plus the bias. And so let's go ahead and do that calculation, and we see that neuron 2 is output of 3. So let's add, I did not add the activation function to this, so this is the first example above, this example here, this example here, and now we're going to add the activation function, and notice how simple the ReLU activation function is in Python. It's just the max between 0. And oh, by the way, if you're not familiar with how to get help in Jupyter Notebook, it's Shift-Tab, and then we can say here's the help on that function. So we're just going to take the max of 0 or whatever the output is for our value. And so in this case, I made a lot of features X inputs and just said, well, what would this look like on the output? So some high-level points to cover here is that ReLU, the rectified linear units, it's fast, it's granular, it's really the most popular activation function that's used, even over the Sigmoid. Sigmoid was often used in the past. It gives greater ability to model nonlinear functions. Also, the derivative is very easy, so you can apply the chain rule, which we'll cover in another lecture in the future about backpropagation, and then how the 2 ReLU functions make a nonlinear functions. So you basically, if you cascade these along a neural net and you multiply that by the inputs, you get nonlinearity. So, and then finally, a ReLU activation function results in a lot of 0 multiplies in your matrix to matrix multiplies. All right, so let's apply this ReLU over these functions and look at the output, and then we take our original example and we multiply that by the ReLU, and we'll take a look at that output as well. Okay. So the observations here is you can represent any number in the real coordinate space, but you need a different activation function at the end, because now the ReLU is, if we applied it to the output, always gives a positive number. So if we extend our example and add more neurons, we will need a final activation that is not a ReLU function. So that's a real important thing to realize. And you get those options when you start modeling in Curis. You can choose your output activation function. It becomes a real important choice in your model. So let's take a quick look at that. So real high level of observation here is the range of your final output value depends on the activation function in your output layer. So if your network only contains ReLU activations, you're going to get you can only represent things in the first quadrant of a XY Cartesian system, right? So it's going to be positive. So some examples of final output activation. So if you have a model, here's all your features, you have a layer here, and then the number of neurons represents the number of classes, and then I want to predict between a range between 0 and 1, and so this higher output here represents my final value, the true value. So this is going to be the class. Now I'm introducing more language here. A class is if we have dogs, cats, and zebras, we have 3 classes. And then we present the features, and then it will classify this into 3 different, we'll say in this case that this was a zebra, because if it was dogs, cats, and zebras, then the one output would be a zebra. So if you have multiple, if you want to predict one class and you have multiple inputs, then this one class, you use the softmax activation. There's a good article that you can link to in the Jupyter Notebook that'll take you to a review of many of these types of activation functions. So let's review what does a softmax do in detail. It's really a normalization of an exponential function. So we have these layer outputs, you calculate the exponential of each of those, and then you normalize that, and then the normalization is basically the value divided by the sum of all these values. So you get a output between 0 and 100%, 0 and 1. So we run that, we can see that in this case, the first value is 90%, 89.95% of all of the output values. So that is the highest probability output. All right, a couple of other activation functions to understand is that if we want to predict a linear output for our final output, you can just use a linear activation function at the end, and that would range over any value, right? It's a linear output. I don't have that as an example up above, but so if your output, your prediction, it can go from negative infinity to infinity, and now you have a linear output, so it's not 0, less than 0 on the x-axis. It's the linear function all the way from negative infinity to infinity, and then your true value will be represented with that linear activation function. Okay, another term here to appreciate is called categorical, predicting multiple labels from multiple classes. So let's go back to you have a dog, cat, and zebra, and I actually want to predict if it is a dog or cat, and here's the 3 outputs, and once again, you have the number of neurons equals the number of classes, where prediction ranges between 0 and 1, and then we have a threshold here that says anything above a certain value, I've got my dog and my cat, right? So it will actually give 2 true value, a binary output of 0 or 1, depending on if you've used a categorical type activation function at the end. So you can see in the deep learning for Python book, there is a table that discusses which activation function to use depending on the type of problem that you have. So if you have a regression problem and you need a numerical value output, your final activation function is linear. If you're doing classification, binary, either it's a dog or not a dog, you want to use a sigmoid. And if you're classifying multiple types of systems, dog, cat, zebra, you use softmax. And then if you're using multiple labels and multiple classes, so you want to recognize, is it a dog or cat in the image, you would use a sigmoid output activation function. So this is to give you a quick introduction to the idea of how can you model a nonlinear features with a linear system. We showed that, and then we discussed and introduced the concept of an activation function. and how the activation function also delivers the ability to make a nonlinear system, so you can recognize nonlinear features in the input, and then finally you need to choose the right activation function on the output to ensure that you have the output that matches your problem. And so this is Introduction to your Deep Learning for Python, Chapter 2 and 3, and you'll cover that in the book, but this was to give you a quick introduction. Okay, until next time.